Now we continue on with the discussion on RMS value and normalized power. Okay, so RMS stands for root mean square. Okay, so it means that we will square the waveform, find its average value, okay, and then take the square root of that average. Okay, kaya siya root mean square. Okay, so the operation, the terms here are actually representative of the operations that are that are to be performed, okay, in the process of finding the root mean square. Okay, so essentially this gives you the formula of finding the root mean square. Okay, so we square the waveform, find its average value, okay, and then take the square root. Okay, now in a circuit where the load is purely resistive, okay, so that would imply that your circuit has a unity power factor. Okay, the average power, okay, of that circuit is given as essentially the average power is given as the square of the root mean square of the voltage divided by R, where R is the resistance of the load, of the resistive load. Okay, or it can also be expressed, the average power can also be computed as the square of the RMS value of the current, okay, times R. And again, R is the resistance of the resistive load. Or it is simply the product of the RMS values of your voltage and current waveforms. Okay, so take note that these equations are consistent with your Ohm's law. Okay, so that is the voltage equals the product of the current and the resistance. Okay, so in example 2, we were able to find the average power, okay, to be equal to the product VI times 2 divided by 2. Okay, and that we mentioned that this is actually, or this can actually be obtained, this product can similarly be obtained by multiplying V over square root of 2 times I over square root of 2. Okay, so ayun, now if we are given, okay, if we are given a voltage, a sinusoidal voltage waveform, okay, which is V times cosine of 2 pi t, okay, plus so we obtain now the RMS value of your voltage waveform, okay, in which again the process of finding your root mean square is square the waveform. So square natin yung let's square the voltage waveform, okay, and then get the average of the squared waveform, average of the squared voltage waveform, okay, and then we take the square root of this average. Okay, now when we square now the waveform, no, so if this is your given voltage waveform, okay, which is periodic for T0, okay, we take note that pag in-square natin si waveform natin, okay, and if it is sinusoidal, the tendency is for the waveform to change its periodicity. Okay, so in getting the average, we won't mind that change in the periodicity or the change in the frequency of your waveform. Okay, so we will still use the original periodicity of your original waveform bago siya ma-square. Okay? So, yun yung tatandaan natin with finding the average of the squared waveform. Okay? So, this is now your squared waveform. Ito. Itong v square may lalabas natin yan. So, we can actually take it out of the integral. So, again, take note na yung lower limit and the upper limit, okay, is the are the boundaries or the endpoints of the interval of your periodic cycle. Okay? And then ang problema natin ngayon is to how to integrate this expression. Okay? So since this is cosine square of an angle, we will use the trigonometric identity. We will use this trigonometric identity here. Okay, so that we will convert this to a double angle formula. Okay, so using this, we will rewrite now this integral, okay, or this integrand, okay, as 1/2 plus 1/2 cosine of 4 pi t over t0. Okay, so yun na nga, nilabas na nga natin si b square over t0. Okay, so now this integral now, okay, this integral can be divided into two components. That is yung integral ng 1/2 dt from 0 to t0, okay, plus integral of 1/2 cosine of 4 pi t over t0 dt from 0 to t0. Okay, so integrating this, that gives you may lalabas natin yung 1/2, okay, and that gets to be multiplied with b square over t0. Okay, so the integral of that is t, okay, wherein we will have to replace t with the upper and the lower limit. Okay, so ayun, while the other half, okay, so meron dito b square over t0. Dito rin merong b square over t0, b square over t0. So ilalabas natin yung 1/2 nun. Okay, so ito, so magiging b square over 2t0 siya. Then to integrate this, we will have to use the balance factor t0 over 4 pi. Okay, then the integral of that cosine is sine, so that's sine 4 pi t over t0. Okay, so in this case we can cancel this t0 out. Okay, so we will have the following. Okay, for the first term, okay, we will have b0 over 2 t0. Now this evaluates to t0 minus 0, which is equal to t0. Kaya t0 yung may iwan dito. Okay, which we can cancel out. Okay, so the first term is left with the factor b squared over 2. Okay, while for the second term, we substitute this here and this here. Okay, so what happens, what will happen is that for the substitution of the upper limit, we will have sine of 4 pi times t0 over t0. Okay, so this t0 cancels out, so that this becomes sine of 4 pi. So ito yun. Okay, while if we substitute now the lower limit, we will have sine of 4 pi times 0 over t0. So yung sine 4 pi 0 over t0 simply evaluates to sine of 0. So ito yun. Okay, now sine of 4 pi is 0, while sine of 0 is 0. Okay, so therefore this factor is essentially 0. So 0 multiplied to this factor makes the entire second term 0. So may iwan na lang talaga. Okay, ang may iwan na lang talaga dito is ito, yung v square over 2. Ito. So the square of your VRMS is the peak voltage square, okay, over 2. Or the amplitude voltage, the voltage amplitude, okay, square divided by 2. Ngayon, the last step in getting the RMS value is getting the square root. So if we get the square root of this, okay, so we'll have V over square root of 2. Okay? Now, if you have your I of t, okay, equals sa I times cosine of 2 pi t over t0. Okay? Tama ba? Yan. Okay. So, if you have your I equals I times cosine of 2 pi t over t0. Okay? At inulit nyo yung proseso na yan. Okay? This time for the current waveform. You would be able to get this result. Okay? So, now, yung palang V over square root of 2 is actually the RMS value of your voltage. Okay? Remember that V here is the peak value or the amplitude of your voltage waveform. Okay? So, dividing your voltage amplitude with square root of 2 gives you the RMS value of your voltage. Same thing, IRMS is the peak current divided by square root of 2. Okay? So, ito yung pinag-usapan natin kanina pa dito. Yan. Kasi kapag kami multiply natin itong dalawa, okay, that gives you the average power to be VI over 2. Which means, yung nakukuha pala nating formula, okay, the average power, okay, is actually the RMS voltage, okay, multiplied to RMS current. If you multiply those two values, you would get the average power. Okay. So, that's your RMS value. Okay. Now, we proceed now with the concept of normalized power. Okay, so we, as communications engineer, we often use that idea. Okay, normally, power, okay, depends on the load of the circuit or on the load that your circuit sees. Yung nakikitang load ng circuit niyo. Okay, now, normalized power means that the power is applied to a load of unity resistance. So, yung circuit ninyo applies a power to a load, okay, whose resistance is 1. Okay? So, yung power na i-apply nyo doon is what we call the normalized power. Okay? So, once naman na alam nyo yung actual load, especially kung resistive naman talaga yung load, okay, that normalized power can be multiplied naman or can be scaled, okay, so that you would be able to know kung ano yung actual power na madi-dissipate dun sa load natin. Okay, so another thing about this concept is to say that the power is given on a per ohm basis. Okay, so kaya dapat kaya ang unit actually ng normalized power, supposedly ang unit ng normalized power is watts per ohm. Okay? It's actually watts per ohm. So, yan yung dapat unit ng ng normalized power. Okay? But we don't normally use that unit for normalized power. Instead, we use the definition. Okay? That is if we have a circuit, okay, having a load of unity resistance, okay, then yung power na i-dissipate ng load na yun, okay, is the normalized power. Okay? So, ang isang quantity that often uses this concept of normalized power is the signal to noise power ratio. Okay? So, in the definition of SNR or signal to noise power ratio, okay, normally, pagka titingnan natin kung ano yung power that your signal dissipates on the load R, okay, and the power that the noise dissipates on the load R, okay. Pagka kinuha natin yung ratio nun, okay, incidentally, that R, okay, or yung resistive load, okay, will cancel. Kasi magre-ratio siya, okay? So, since, parang, so that, we will be able to, compute the signal to noise power, okay? We will, the R, okay, or the value of R would cancel on that ratio, okay? So, but sometimes, yung ratio na yon is actually inaccurate, okay? Because of, yun na nga, the idea of the normalized power. Okay, so the idea of normalized power, okay, is useful pagka yun nga, magko-compute tayo ng powers, and then we don't really know, or we don't really have an idea on the characteristics of the load that your circuit that will dissipate the power. Okay, so ayun na nga, when we need the actual value for the power, okay, you can actually denormalize. Okay, so if you are using normalized power, and at the end of your calculations you need the actual value of the power, okay, if you now know the resistance of your load, then you can denormalize, okay, by multiplying the normalized power with the resistance of the load. Okay, we also observe, okay, that the average power is V square RMS over R, okay, or alternatively it can be I, the square of the RMS current, okay, times R, okay. If you actually set the resistance equal to 1 ohm, okay, then you would have the normalized average power. So the normalized average power here is simply the square of the RMS voltage, or the square of the RMS current. Okay, so this is now what we call the normalized average power. Okay, so again, ang paggamit ng normalized power, okay, is dependent on how much of an ease you would like your analysis to be. Okay, so kung medyo that R actually causes your analysis to be kind of difficult because of its value, then you can use normalized power. Okay, so that. So now we classify now your waveforms into energy and power waveforms. Okay, so a waveform is a power waveform, okay, if the normalized average power is finite and non-zero. Okay, is finite and non-zero. Okay, the waveform is energy, or is considered to be an energy waveform if the total normalized energy is finite and non-zero. Okay, so how do we find the total normalized energy and the total normalized power? Okay, so essentially the energy is the sum of squares of your waveform values. Okay, so we will add up the squares of your waveform values, okay, from certain limits. Okay, so add up sa continuous waveform means integration. Okay, and then we will evaluate the limit of this expression. We will evaluate the limit of this expression as your t approaches infinity. Okay, so if we would like our or if we would or based on this formula, okay, based on this formula, E would be considered or would be finite, okay, would be finite and non-zero, okay, and thus would imply that waveform, okay, waveform W is an energy waveform, okay, if your waveform, okay, if your waveform actually approaches zero, okay, as t approaches infinity, okay, so that is magiging finite at non-zero ang energy ng isang waveform kapag ka ang kanyang values, okay, is approaching zero, okay, as your t approaches infinity, okay. So which means, okay, kung ang waveform mo ay time limited, okay, if your waveform is time limited, meaning it only is non-zero, your waveform is non-zero for a certain interval of time. Okay, say for example, yung waveform mo is non-zero, okay, for a certain range of time from T1, okay, hanggang T2, okay, while it is zero, okay, otherwise, okay, then your waveform is time limited, okay, time limited siya because it is only defined for a certain interval of time, okay. This kind of waveforms is considered or is characterized as energy waveforms, okay. So ito yung mga waveforms na merong finite duration, okay. And we take note or we observe that any physically realizable waveforms, so any waveforms na pwede nyong i-generate sa laboratory or using circuits, okay, or using computers, okay, are finite duration and therefore are energy waveforms, okay. So practical waveforms are energy waveforms, okay. So although may mga waveforms tayo whose mathematical model imply that the waveform has an infinite duration, okay. But as long as the value of your waveform approaches zero, okay, as your time approaches infinity, okay, you can still consider that waveform to be an energy waveform, okay. So probably itong definition na to would apply for model waveform, okay, or mathematical model of your waveform, okay. That, okay. So ayun, now so ito yun, no, ito yung sinasabi ko, physically realizable waveforms are of energy type, okay. But since we'll often model these waveforms by infinite duration, okay, most of the waveforms that we will have to deal with are of power type, okay. So here's the thing, no, your waveform is either an energy or a power waveform, okay. They cannot be both. Hindi siya pwedeng magsabay na energy tsaka power siya, okay. So it's either just an energy waveform or just a power waveform, okay. So which means pag classified na siya as energy waveform, okay, its average power, okay, is now infinite, okay. Kaya dito, if your waveform is now classified as an energy waveform, okay, we know that its energy would be finite, okay, and non-zero, and its power would be infinite na, okay. So, ayun. However, okay, waveforms, okay, that persist or that has non-zero values for all values of time, okay. So waveforms that persist for all values of t, okay, is considered to be a power waveform, okay. And if you classify a waveform to be a power waveform, okay, it would have a finite average power, okay, but its energy, okay, is now considered to be infinite, okay. So yung mga waveforms that again persist over time, okay, are used as models, okay, for waveforms for simpler analysis. So tatandaan natin yun. Ginagamit natin usually ang mga waveforms that persist over time, okay, as mathematical models, okay. That is to aid us in simplifying the analysis of the signals and the systems that would ensue, okay. So again, if this persists over time, so alam natin that these waveforms are infinite duration waveforms, okay. So they have infinite duration, okay. So an example of a waveform, okay, that falls under here are those that are periodic waveforms, okay. So since the model that we will use in the analysis are more or less infinite duration and are therefore of power type, okay. Yung mako-compute natin theoretical values ng average power at saka RMS value, for example, okay, may may return some yung laboratory instruments that we use, okay, that measure average quantities. Again, these quantities presupposes that your waveforms, okay, are of power type, okay, or of infinite duration, okay. Actually measure this as average, okay, over a finite time interval, okay. So therefore, yung ina-average ng instrumento or ng laboratory instruments natin, okay, depends actually on how long, okay, the duration of the signal, okay, that is being sampled by the instrument, okay. So therefore, kasi supposedly kapag energy kasi yung signal natin, okay, kapag energy type yung signal natin, which is yun nga yung mga physical waveforms natin, okay. Supposedly kapag energy yung signals natin, we should not be able to compute these average values using the time average operator, okay, because the time average operator assumes that your t, okay, or the duration of your signal is infinite, okay. So since practical waveforms have their duration truncated, okay, instead of mahaba yung duration niya, finite lang yung duration na, okay. Those laboratory instruments that measure this or the measured average quantities, okay, that we compute here, okay, may actually be for for energy signals, okay. So ayun, So we have to be very careful, okay, with how we interpret yung theoretical values at saka yung theoretical values and instrument values natin. Anyway, these instrument values naman or work, they do work in a manner that assumes, okay, that your waveform is actually of infinitely long duration. Okay? Pero hindi naman talaga siya infinite long duration. Mahaba lang siya in the sense na mahaba lang yung duration niya in the sense na for kumaga relative to, okay, relative to a certain mahaba na siya. Okay? So ayun. So that is why yung makukuha nating theoretical average quantities, okay, yung nako-compute natin using the average operator, the time average operator, will still be reliable and will be near that of the readings of your laboratory instrument. Okay? So there. Another measurement, okay? Another measurement that is important for communications engineer to understand is the decibel. Okay? So we normally use decibel, okay, to express logarithmic measure of power ratios. Okay? The thing is, yung power kasi natin, okay, yung power levels natin may be very large at the transmitter side and very small at the receiver side. Okay? So, pag kinumpare natin yung absolute ratios nila, that would give us a very large quantity. So that is why instead of using a linear scale, linear scale for these power ratios, we use logarithmic scale. Okay, para hindi masyadong malaki yung figures na nakukuha natin. Okay? So decibel is the unit that we use to compare, okay, the logarithmic difference of powers, okay, between two points in your system. Okay? So say for example, the decibel gain of a circuit, kung meron kayong circuit na okay, has a that takes in power in or P in as an input, okay, and then produces P out at the powers at the output side, okay. The decibel gain of that circuit, okay, is given as the ratio of the powers at the output and the input sides. Okay, then kunin natin yung base 10 logarithm nung ratio nila. Then multiply natin with 10. Okay, so actually this ratio is simply as the unit bell. Okay, itong ratio na to, ang unit niyan bell. Okay, bell lang yan. Okay, kaya lang bell actually is too large of too small of a quantity pa. So we multiply it by 10. So ang standard na ginagamit natin for comparing powers is decibel. Okay? So now, if power now involves or if power here, okay, say power out is the RMS voltage out, okay, square over R load. Yung load dito sa side na to. Okay? So that's R load. Okay? While ang power in natin is the voltage, okay, RMS in squared over the input impedance of your circuit. So yung circuit niyo has an input impedance R in. So you can measure VRMS squared there. VRMS there. Okay. So this is your VRMS in. While makakapag-measure din tayo ng Vrms out sa output side. Okay? So in that case, we can convert this, okay, into this ratio. Okay? So we have 20, magiging 20 na ngayon since we are now comparing voltages. Okay? So as you can see, yung decibel ninyo, okay, has a multiplier of 10 if you're comparing powers. Okay? But if you're comparing voltages, okay, if you're comparing voltages or currents, okay, the multiplier becomes 20. Okay? So, ayun. But still, the unit there is decibel. Okay? Now, on the concept of normalized power, okay, that is, yung power natin has, we consider this, this load, okay? We consider this R load, okay, and this R in, okay, to be of unity resistance, okay? These formulas would simply reduce to this one, these terms, okay? So, ayan. So, ito na ngayon. If normalized powers are used, we will be reducing equation 12 into this, okay? So, we take note or we observe that this equation will not give you the true value for decibel. Okay? Since we really don't know what R in and what R load, the values of R in and R load are. Okay? So, but just to simplify again, just to aid us in simplifying our analysis, if it would help us to set these two to be equal and equal to 1. Okay, then it's okay it is okay as a practice, okay? Kung mapapadali yung yung analysis natin. Okay? So there. So even if these decibel values will not be as accurate as we need them to be, or as accurate as they should be, okay? Hindi naman masyadong malalayo yung hindi naman masyadong malalayo yung computed value if we set R in equal to R load. So, ayan. So, converting from decibel, ratio, okay, or decibel, decibel ratio ng power, okay, decibel power ratio to absolute power ratio, okay, we will use this formula. Okay, so, power out over power in equals 10 raised to, yung value ng dB, divide natin ng 10, tapos we will use that as an exponent to the base 10, okay, and that gives you the absolute ratio, okay. So this is now the absolute power ratio. Power ratio. Okay. So, there. So, now, one important measure of circuits used in communication systems, okay, especially yung mga transmitter tsaka yung mga those that transmits, okay, or produces signal to that needs your signal to be transmitted, or that needs your information to be transmitted, o kaya receive naman, okay, is what we call yung signal to noise ratio. Okay, so it is important for us to understand yung konsepto ng signal to noise ratio. Okay, so simply put, okay, signal to noise ratio is the ratio of the power of the signal or information bearing signal, okay, to the ratio of the power produced by your noise waveform. Okay, that is on a circuit, okay, on a circuit, once mag-input tayo ng waveform dyan, okay, once mag-input tayo ng waveform dyan, the circuit may introduce noise signal or noise waveform. Okay, pwede siya mag-introduce ng noise waveform dun sa sa circuit natin. Okay, so essentially yung circuit niyo becomes something like this. Okay? So, ito yung waveform ninyo. Ito yung noise signal ninyo or noise waveform ninyo. Okay? The addition of them, okay? Ito yung buong system niyo, no? Or buong circuit niyo. Okay? So, the circuit essentially adds the two. Okay? The two waveforms. Okay? And then, processes the sum. Okay? And then produces an output waveform. Okay? Say that output waveform is y of t. Okay? Now, this y of t, okay, both contains your information, your process information bearing signal, okay, and your noise waveform. Okay? Now, assuming na linear itong circuit natin, okay, we can actually separate the power of this, the power that will be dissipated by this information bearing signal, okay, to your load, okay, and the power to be dissipated by your noise waveform to the same load. Okay? Ngayon, yung performance ng circuit na to is indicated by this ratio. Okay? The ratio of the average signal power over the average noise power. Okay? Mas mataas ito. Ito yung tinatawag natin ngayong SNR. Okay? Signal to noise ratio. We would like your SNR to be high. Okay? Because we would like your information bearing signal to be more or to bear more power or to possess more power compared to your noise. Okay? So that yung ratio niya dapat mataas. Okay? So in decibel, we express that SNR in decibel to be 10 log. Again, this is power ratio. So we're comparing two powers. So we will use 10 as a multiplier. So 10 times log of P signal or average signal power over average noise power. Okay? So, if we represent your signal, information bearing signal with the waveform S of T, so this is your info bearing signal. And your N, so dapat pala S pala ginamit ko dito. So this should be S. Okay. And your N to be your noise waveform. Okay. So the average signal power, okay, is the RMS voltage, okay, the square of the RMS voltage over R, okay. So we compute the RMS voltage of your signal to be the square of the waveform, then the average of that squared waveform, okay. So yun yung VRMS square, okay. So yung noise power naman would have noise voltage or RMS voltage, okay, using the same operation. Again, square the waveform, and then average the waveform. Okay, this gives you the VRMS square. Okay, so if the waveform is actually a voltage, okay, so kung current naman yan, then the result is the RMS value for your current squared. Okay, so in terms of RMS voltages, okay, we can compute your SNR or your signal to noise ratio in dB, okay, using 20 log VRMS of your signal over VRMS of your noise. Okay, again, since we're comparing voltages, we will use the ratio or the factor 20. Okay, so there. Okay, so that's how we compute for the SNR. Okay, in absolute terms and in dB terms or in decibel terms. Okay, so other uses or other things that we can use your decimal or your decibel measure for is to indicate absolute levels of power with respect to some reference level. So kung i-fix natin yung say for example, we have here dB, no? The general formula is dB equals 10 log of a power level, okay, divided by a reference power level. Okay? Kung i-fix natin ito, then our dB, okay, will have some special names. Okay? Say for example, if your reference is 1 milliwatt, okay, this one, okay, your decibel becomes now dBm. So, ibig sabihin, dBm means power ratio, okay, or power level relative to 1 milliwatt power. Yun yung ibig sabihin ng dBm. Okay? So, if we're to compare dBm with dB, okay? If we have to compare dBm with dB, so ito yung paggamit ng dBm at saka ng dB, kasi ang dB kasi we use this as power ratio. That is, we compare two powers. Okay? If we compare two powers. Okay? Usually, ang dBm or dB tapos yung unit na may nakadikit dito. Say dBm, dB W, okay? dB K, at saka say dB micro, okay? And so on. Ito, we don't use this as power ratio. Okay? So we use this as actually power levels themselves. So ibig sabihin, pag nagsabi tayo ng say for example, 1 dBm, okay? I'm actually referring to a power. Okay? Or a power level. Okay? Which is 1 dBm means 10 times logarithm of that power, okay, kung naman yung power na yun, divided by 1 milliwatt, okay, so that's 1 e raised to negative 3 watts, okay, so this is 1/10 times 1 milliwatt, so this, yung power na pinag-usapan natin dito is 0.1 milliwatts, okay. So, ibig sabihin, yung 1 dBm refers to 0.1 milliwatts, tama ba? So, we divide this by 10, so 0.1. Okay? Then, we multiply it by 1 milliwatts, so 0.1 milliwatts. Okay? So, 0 dBm, okay, actually refers to a power level of 1 milliwatt. Okay? So, power level talaga siya. Okay? Whereas, ang dB kasi, power ratio yan. It is used to specify gain or attenuation. Kung gaano itinaas nung power level mo at one side of the circuit to the other side of the circuit. Okay? Or kung gaano binaba yung power levels at one side of the circuit to the other side of the circuit. Okay? So, ayun. That's one thing that you have to remember here. Okay? We don't really use this this dBm, dBW, dBk, and dB micro, okay, to indicate ratios, okay, or to indicate comparison of powers. Ginagamit talaga natin siya to express powers with themselves. Okay? So, it is possible, okay, well, it is possible that since say for example, dBm denotes power level, okay, and dB denotes gain, for example, then it is possible na i-add nyo itong dalawang to. Okay? Say for example, in a circuit, okay, in one circuit, okay, in a circuit with a power input, okay, with a power input of 10 dBm, okay, the circuit provides a gain of say 30 dB. Okay, it provides a gain of 30 dB. So the power output at this side of the circuit is simply 10 dBm plus 30 dB. That gives you 40 dBm. Okay? So, ganun yung operations nung dB at saka dBm natin. Pwede nyo i-counter check yan. The actual power level at this side of the circuit is 10 raised to 10 over 10. So this is 10 milliwatts. So yung power input is 10 milliwatts. Yung gain natin, okay, is 10 raised to 30 over 10. Okay, so that's 10 raised to 3. That is 1,000. Okay. 10 times 10 is 100 times 10, 1,000. Okay. So ngayon, ang mangyayari dyan is that the power output at this side is this one times this one. So 1,000, okay, times 10 milliwatts. Okay. So that should give us, itong 1,000 kasi, itong milliwatts ito, would cancel each other out. Okay. So parang 10 milliwatts, 10 times 10 raised to negative 3. Okay. So, or say 10 milliwatts is 0.01 watt. Okay? Yan. 1, 2, 3. So, that's 10 milliwatts. Okay? So, multiply natin ng 1,000 yan. We will have to move this for 3 times. So, 1, 2, 3. So, the power output is, seems to be 10 watts. Okay? Yan yung magiging power output natin. Okay? Ngayon, pag kinonvert nyo to sa pag kinonvert nyo itong power output na to sa dBm, okay, that is 10 logarithm of 10 milliwatt divided by 1 times 10 raised to negative 3. Okay. That should give us 40 dBm. Okay. So, ito, yung nakuha natin dito. So that's how it works actually. Okay. So if your decibel carries a unit, okay, or a prefix, okay, mk per kilo, namagit ko siya dito W for base unit, okay, micro for microwatts, okay, and so on. These are power levels themselves, okay, while dB is a ratio. Okay, so ayun. There are also versions of this on voltages and currents. Okay. Say for example, ito. Meron tayong dBmB. Okay. So dBmB, okay, is a voltage level naman. Okay. dBmB is voltage level. Okay. dBmB is voltage level reference to 1 millivolts. Okay. Naka-reference naman niya sa 1 millivolts. Okay. So, itong correspondence na to, okay, the 0 dBmB corresponds to negative 48.75 dBm. Actually, hindi yan equal. Okay. Because, remember, that this is a voltage level. Okay? This is a power level. So, magpapareho lang yan. Okay? If this power or this voltage, okay, produces this power at a given load. Okay? So, you can actually, verify that, correspondence, okay, using that P equals V Rms square over R, and then use R equals 1 ohm. Okay. So,